Hello everyone, I'm Pratap here. Welcome all of you to a wonderful class today. We'll discuss Markov jump process and Kolmogorov equations. When I say equations, I'm talking about Kolmogorov's forward differential equation, Kolmogorov's backward differential equation, Kolmogorov's backward integral equation, and Kolmogorov's backward differential equations. Why we use these differential equations? If you remember, I started the class with Kolmogorov equations. When we talk about discrete time stochastic process, we use Markov chains. And in Markov chains, Kolmogorov equation is sufficient. However, when we go to continuous time stochastic process, without these four equations, we will not be able to do anything. Remember, it's so important for you if you are doing some kind of statistical modeling. It could be actual science or anything. There are only two frameworks. One is random variable and the other one is stochastic process. These are the only two frameworks available. Either you have to start with a random variable. You must have studied everything in CS1. Even in CS1 also we'll use in loss distribution. All the distributions you will study. Gamma distribution, Bird distribution, Weibull distribution, all the distributions will use random variables. Coming to stochastic process, that is the other framework. Here there are two types. We use time dependent. We'll study here in time series and in this chapter. And also there is space dependent called temporal and spatial. But that spatial we are not doing now. We'll concentrate on time dependent. When I talk about continuous time stochastic process, probably today for the first time I will introduce how to use this framework where your time is continuous and space is discrete. Whatever I taught before now, there our time was discrete and state was discrete. And we defined Markov chain. Today we'll do something where your time is continuous, but states are discrete. Today at the end of this class, you will be amazed to know how useful these equations are. Can you imagine you are seeing a movie, okay, and we are talking about frame by frame. We will be forecasting future in continuous time. It will be a wonderful class for you if you attend full class and try to understand. And then you will definitely see what is the value of Kolmogorov's equations. Can you imagine? World of opportunities will be for you if you master this concept. This is the framework. I'm talking about stochastic process applications. And now here in CS2, we'll be doing continuous time discrete step, where we are talking about Markov process, Markov jump process. But when you talk about continuous time and continuous state, then you have to go to CM2, the applications in stock market. Stock price you want to know next moment, not next day, not next month. There you have to use Brownian motion. In today's class, you will see how important it is. I will make it very, very easy for you with a very simple example. Let's get started. Today, that is 27th of January. Okay, we are here. Today we are here, 27th of January. I will take 1 day gap. I will take 1 day gap. Now suppose this is 28 a.m. Okay, 8 a.m. on 27th January 2026. This is my framework, the stochastic process, where I will use a model. For random variables, we use Poisson binomial distribution. Here, we'll use Markov chain. This is my proper framework, my stochastic process, where I can run a model like Markov chain. Okay, this is my model, and my framework is stochastic process where the index is time. Anu here. So this is Anu. Anu is a moody girl. Okay, Anu, this is Anu. See, Markov and Kolmogorov today you will understand. This is Anu. And this is Amit. See, time also I have to write. So because between 20 to 21, 20 time is 27 January. 21 time is 28th January. Okay, now we are probably at 6:23 p.m. 6:23 p.m. Okay, So according to time, this is now, this is present, okay, 6:23. Now this is 8 a.m., this is 6:23 p.m. 6 p.m. let me write 6 p.m. Now here we are, here I am now, okay, I am now here. This is my present. So now according to Markov, Markov says, if you want to know Anu's mood, okay, mood, let me write mood. This is happy, H, this is sad, happy, sad, happy, sad, happy, okay. Two state, as I already mentioned you, discrete time, discrete state. We want to know tomorrow at 8 a.m. Listen, this is so important. Tomorrow at 8 a.m., what is the mood? What will be? There are two states. Anu is either sad or happy. Okay, now Amit is asking me, can you say now, I want to know tomorrow at 8 a.m. before leaving to the company, what will be her mood? Amit is asking now. I'm saying, yes, I can answer. Then Amit is saying, how can you answer? I'm saying, because I know Markov chains. Okay, how can you answer? You say me now. What I say is, I need some information. Markov says one step information we need. Markov says, if you know where you are now, one step, we are talking about one step. Now means it's 20 times, 8 a.m. Now I will ask, see the red dot here. Now I will ask, you know what? If you can say today's information, I will be able to forecast for tomorrow. Okay. If you say me today's information, I will be able to say something about tomorrow. Okay. So it could be like this, and it could be like this. Okay. So now I'm asking, Amit, did you watch today? Amit says, yes, today she was happy. Now tell me about tomorrow. I say, okay, let me bring my transition matrix. My transition matrix is this. Happy, sad, happy, sad. Today, tomorrow, the gap is 1 day. Okay. Equal duration is very important for this framework. Now, this is 70%. This is 30%. This is, you can take any, to 20%. Say something like this. Okay. So what will happen is, I will use this matrix, this transition matrix, and I will use this information. Then I will be able to say something for tomorrow. So I'm predicting for tomorrow. Okay. This is one step ahead forecast. This is what? One step ahead forecast. I want to forecast for this time. Oh, yes, from here. Here means I have information. See, from here, any point between these two, what we need is, I need to know the information. So you are here or here, it doesn't matter, right? Anyway, so now I should be able to forecast this. Is it possible? Yes, it's possible. It's possible. See, H to H probability is 70%. And today I know the information. I mean, happy means what? It's 1-0 probability. So I'll multiply 1-0. This is 1-0. And this I will multiply 0.7, 0.3, 0.8, 0.2. Multiply. Matrix multiplication simple. So this is 0.7. And this one is 1 multiplied by, then 1 multiplied by 0.30. That is 0.3. Okay. So what I'm saying is, there is a 70% probability. See, we can't say for sure 100%. See, there is a difference between God and actuary, right? What actuary thinks he is a God, but God never says he is an actuary, right? God can only say tomorrow exactly 100% certainty, probability, but we say probability 70% chance. What about day after tomorrow? Staying here, not tomorrow, staying here now only. We have only one step information. Yes, we can continue. 0.7, 0.3, 0.8, 0.2. Again, My assumption is this is homogeneous Markov chain. Okay. I will also compare today between Poisson process and Markov process, but for that we have to go to continuous time. Okay. That also Poisson process also not over. In every class it will come because they are very close, Markov and Poisson. And all the properties will borrow, I mean, kind of from Poisson to Markov. Markov is a generalization, you can see. Acha, 0.7, 0.3 p multiply, this is 49, this is 24. 49 plus 24, 50, 23, 73. 50, 23, right? Yeah, 73. See, it's increasing. Okay. That way probabilities, okay. If it's correct, 2, 7. Okay. So now, if we have this information, then we'll be able to say for tomorrow in terms of probabilities. Done. Okay. Up to this, it's done. I didn't teach anything new. I already completed this one. Now, Amit says, sir, you tell me one thing. If you are using this information, why Markov is leaving all the past information? See, where you use this information, past information, is the past information is useless? I mean, why Markov said something like this? I don't understand. I studied it once, but I have no idea what I mean, so much information. You have 100 days, 1000 days information you have, 10,000 days information you have, but you are using only one step and you are answering. Why? Even why Markov said that way? Why Markov used only one step? Suppose you want to forecast stock price tomorrow, will you use only today's information or you use the past history? Again, coming here, it's not that we are living. Markov says, this see, what we did is this transition matrix. How we got this transition matrix? Now we are taking it as a problem. But these transition matrix probabilities, how you will get these probabilities? 0.7, 0.3. This is also part of the course. This is called estimation. You need to estimate from the past. The past will be useful. But when you are answering, okay, like at inference stage, at answering stage, you are sitting in a table, you want to answer, there will use one. And you have the transition matrix. Use the transition. But to estimate the transition matrix, the past will be used. The realization, whatever way the stochastic process run by now, that will use, there will use. So here, whatever state, here this is one thing. Other thing is this information is anyway used. It's not that it's not used. Okay. Markov chain. Now we are talking about Markov chain. Over, done. Up to this, it's done. Nothing is new. Again, if you are asking, you never taught this one how to estimate. Yes, this is very important. You get an exam question. We'll do that. When I'm completing the main concepts here. Okay. So if you want to do now, you can go through my already recorded videos I uploaded on YouTube. If you don't find any concept, you ask me. I have recordings, I will share with you. Okay, you write in the comment. Now coming back to this one now. From here, I'm starting today's class. Amit says, Anu is now coming. She's on the road. She called me and she said she is coming now. Tomorrow anyway, you said. Can you say, now means it's time 6:35, 7 p.m. Probably she will reach at 7 p.m. now. This one, okay? This is the one step. Two step means you have to find P. Anyway, I did matrix multiplication. I'm not going to that. Now, the question is, here she is coming. Okay? Now, this one will delete. Okay? We'll delete this and we'll delete this. Now, instead of tomorrow morning 8 a.m., that already we studied when I taught you Markov chains, how to model that one. But now, Anu is asking, sorry, Amit is asking, no, Anu is coming now here. We want immediately after half an hour. Can you predict here? Is there any chance that you can predict here? That's a great question, right? Can I predict here? Oh God. See, when I started the class, I said that equidistance, the distance between the time points must be equal. But now it's not equal. Suppose tomorrow morning 8 a.m. and now is the time. What is the time now? Now is 7 p.m. So it's 11 hours. But what we studied? 8 a.m. each day in the morning. Okay, that's what is important. If I know today at 8 a.m., I can only say tomorrow at 8 a.m. Okay, even using this in our general insurance, okay, there is a concept of experience rating I explained last time. That is year by year we see. Okay, always you see there could be around 50 problems. You should solve 50 problems. You know what? For the exam, 50 problems you need to solve. There are very awesome problems using this Markov chain. But in this question, can I say the mode after half an hour? That means 7 p.m. 7 p.m. is only 11 hours since morning 8 a.m. It's not 24 hours. It's not one day anymore. Remember the transition matrix today, tomorrow. This is present, this is future. This is present and this is future. But in our case, this present is today, future is tomorrow. So today, tomorrow, tomorrow to day after tomorrow, today to also day after tomorrow. That is two-step ahead forecast. Matrix multiplication, right? You go on multiply matrix. And in cases where in terms of probabilities are given, you can directly find, right? I hope you must be knowing directly finding. When I say directly finding means this. Instead of doing these two matrix multiplication, because you know the exact position, what you can do is you find p square h to h. This probability you need. That's all. H to h. Okay. This probability of p square. You find p square matrix, then h to h. So p square matrix you can find, that is two step, and you can find this. And directly you can answer h to h in one step, that is 0.7. Okay, we got 0.7 here also. Then you must be asking, then there are two methods. In all problems we use two methods. No, you can't use. Suppose here I know the information. Okay, Amit said me the information, then I'm forecasting for tomorrow. But suppose you don't know the information. Okay, you know only in terms of probability. This is not 1001. This is say something like 0.5, 0.5 or 0.1, 0.9. Okay, again, like Amit says, sir, I don't know exactly today whether she was happy or not. I saw from a distance, but I felt as if like she was sad. So I can say sad 90% probability and H zero point 0.1 probability. And then what will happen? You have to use matrix multiplication. You can't use p square. You have to multiply this probabilities 0.1, 0.9, 0.1, 0.9, and then go on multiplying. There, this p square, p power 3, p power 4, those will not be useful. This is also another thing, distinction. Remember, you can use p power 2, p power 3, p power 4, p power 5 when you know exact the probability is 1, 0, 0, 1. Okay, in three states, 1, 0, 0. That way it's given. Total probability is 1. However, if you don't know this one exactly, you know in probabilities, then you have to use matrix multiplication only. Anyway, let me go to my original point. Now the question is I need to answer here. So what I can do? Who can help me now? Because I learned all the time Markov chain, stochastic process, discrete time stochastic process, discrete state stochastic process, dynamic modeling. It's not a static modeling like random variable. What I will do? Where I will go? How can I answer Mr. Amit? Amit is eager to know. Then Kolmogorov comes to my rescue. Kolmogorov says, no worries, my friend. He is no more here. Kolmogorov said, yes, it's possible. Instead of defining every day, you can make it every moment. That is called continuous time stochastic process. Continuous time stochastic process. Okay. Let me now go to continuous time stochastic process. What I will do in continuous time stochastic process, I will delete all this. Continuous time. Okay. Continuous time. Continuous time. No, these are not required. Okay. This you can write 21, 22, not a problem, but these are not required. Continuous time stochastic process. There is no gap. 5 equations. Okay. Now the first one is Kolmogorov's equations I will teach today. Okay. This is for Markov chain, normal Markov chain, discrete time, discrete state. Now these are the 4 we will study in the next two days and 2 more classes, 2, 3, 4, 5. Here comes Kolmogorov's forward differential equation. So why differential equation? We'll go to that. Kolmogorov's backward differential equation. Kolmogorov's forward integral equation, where integration will be there. Then Kolmogorov's forward backward integral equation. These are the 4 equations we'll study. So what we will do, we'll form Kolmogorov equation, we'll solve Kolmogorov equation. I will show you now one. Okay, I will show you now. Then I will go back to this problem. Okay, so that your clarity will be 100%. Okay, you learn conceptually. So here in continuous time, we'll be needing this. In discrete time, I will explain how and why. In continuous time, we'll be using this. In discrete time, we'll be using this. We already use. I will just write the equation. Okay, that's all. Nothing more than that. If we model this in continuous time, then we'll be able to answer continuously. We are here. Okay. And we want to be here. We want to be here. In how many times? In, let me write here, 1 time, 2, 3, 4, right? You know, I mean, if you know for sure that it's 100 probability, then p power 3. If this is a transition matrix here, considering that it's homogeneous, pq you have to find, then 1, 2. Let me write the straight numbers 1, 2, 3, 1, 2, 3. So you can find 1, 2, 3, 1, 2, 3. Okay. So what is Kolmogorov's normal equation? No differentiation, no integration. Okay. Kolmogorov's normal equation says probability that you will go from I to j. Okay. And you go from m to n like this. I to j you will go here. I is 1 and j is 3 here. 1 to 3 you want to go. In how many time periods? M to n. Okay. The notation also I will show you once. I have already notes. This was 2015. Okay. 2000. Acha, yeah. I taught online only. I just saved it. If you see where I've written this PIJMN. Okay. This symbol I'm saying. PIK and PKJ. This is Kolmogorov's equation I'm saying. M, L, and this is L, N, this one. Okay. I showed you. See, PIK, KJ, ML, LN, K belongs to S. Summation K belongs to S. I will explain you why summation. Now, let me write summation. This is Kolmogorov's equation, normal equation. And this is for Markov chain. See, this is discrete state, discrete time, discrete state. And over K, I'm writing here. Over K. Over K means what? Achha, first of all, if you want to go I to J, in how many steps? M to N means 1 to 4, 3 steps, the difference, right? So you can write 1 to 4. 1 to 4 means total 3. In homogeneous, we don't need this. You can directly write P. Yeah, here I've written. This is 3 steps. This one, this 3, it could be 2 also, right? I've written 1 because I'm saying you are here. That's why this is 1. This 1. This 3 means you want to go here. That's a 2. 2 I've written. Okay. 2. You want to go here. So let me write 2 in 3 steps. You want to go from 1 to 2. Not like this. Not like this. I mean, this diagram is wrong because you have to go through states only. Okay. These are allowed. Not randomly like this. I can write it. What I can do is I can write like this. I can write like this. Then I can write like this. Then I can write like this. This is one way. Similarly, you can write from here to here. It's not Poisson process. You can go 2 step also. No problem. You can come down also here to here. Acha, 1, 1, here to here. Then you can go from here to here. In Poisson process, the increments are only 1. In Markov process, from any state, you can go to any other state. It's a stochastic process. Basically, the only thing is one step dependence. We take only one step information to predict for future. You want here to here. You want here to here. Okay. So there are so many ways. It will take a lot of time if you do manually. Suppose there are 3000 states. Okay, it will take a lot of time, right? In homogeneous, you can just write the difference, Mn difference. Okay, I'll change this one now. That is equal to summation. I will not change k here. P I k I will keep. I though I can write 1k ml. Then p k j is now 2 sorted out. J is 3. J is 2. Okay, 1 to 2. And here M to L, L to N. Acha. M to L, when we say L to N, first of all, you have to go to L, then L to N. Okay. So summation over K. Suppose you say that you will go from here to here. Then you want to go from here to here. Again, that means again you have to divide this in two parts. That is separate thing. But now, not in terms of diagram, just think that you are planning to go. Acha, I will do this now. That's better. So 1 to 3 in one step and 3 to 2 in another 2 steps. I have divided. Okay. And this one how to do, again you can apply. See, there is something called recursion. Continuously we will be using recursion here. Okay. And in Kolmogorov forward and backward, I will explain you what is why we say forward, why we say backward. There, this will have meaning. Just remember this, and then you have to go from this to this. Acha. When you have decided that this is one step and this is one, this to over one step. This one again, if you want to do that, again you have to put here and again you have to write this. That is a separate thing. Okay. So to make it easier, I can delete one step so that I will say 1, 1. That's all. Okay. But there are 3 states here. Remember, there are 2. Anyway, that right hand side I'm leaving. What is summation over k? Or maybe suppose if you have any hesitation, I can delete this for now. So what is k here? K could be, see, you can go like this, then you can plan going this. I mean, not this way, but through some state. Okay. Or you can go here, then you can plan how to go. See, you went from Delhi to Kanpur. Now from Kanpur to Bangalore, you want to come. Okay. So there is a lot of way. Again, from Kanpur to Hyderabad to Bangalore, maybe. Or Kanpur to Chennai to Bangalore. Here you went from Delhi. No, you are in Delhi only. Okay. In the next time period, you didn't move. And from Delhi directly you want to go to, in two flights, you want to go to this number 2, say Bangalore. Okay. So you stay again in one time period Delhi, next time period you leave, or you go to some other place, Chennai, in one day, another day you go to Delhi. So there are again so many, right? So all these paths we have to add. Okay, if you consider only 3 times, then to directly here only you will manage. Okay, if you have 4, now we have divided, at least we have divided this one, and here you can say I have rest. Okay, then this one again you have to put here, again you have to do. But if you have 3, suppose it's like this, it's pretty clear. If I make it 3, then what will happen? Cut. Okay, now things will be easy for you. Now also this one also not required, this one not required, this one not required. It will be little bit easier for you. I mean, one you need to understand. Okay, now where this summation comes actually, you want to go, suppose here to here, 1 to 2 in 2 time periods. Here I will make it 2, here 1 to 2. So the summation, how I will write? I will write the summation that is equal to, in the summation form, this summation over k means I will write P1 to 1, P1 to 2 plus P1 to 2, P2 to 2, plus P1 to 3, P3 to 2. Okay. So here this is one, this is the first one. Probability that you will go from here to here, then here to here. 2, 2. We are multiplying 2 probabilities, right? So you multiply this probability, that is one multiplying because and this and this. There is another path. You can go this way also. So plus or this is or not and this plus or this and this. That's all. Okay, clear. This is only our Kolmogorov's equation. It's not that Kolmogorov's equation is not used. It's used in Markov chains itself in discrete time, discrete state, stochastic process. Now we'll go to continuous time. Okay. Now we'll go to continuous time. Let me go back here to our original example. This is continuous time now. Let me erase all here. Okay. Let me erase all here. This is continuous time. This is continuous time. Erase all. Done. This is done. This is done. This one done. This one done. Delete. Okay. Now see, I said continuous time. Continuous time means all these times are there continuously. This one also, this looks bad. So this also delete. This one will no more be there. Okay. Instead of this, we'll be needing, okay, let it be. But we'll delete something so that it will not look clumsy. Okay. So I deleted all this and I will keep whatever required for this. Now, actually, we'll study how to manage continuous time. It's so important. And I will show you one example. Okay. That will enlighten you if you didn't know by now. I hope your students also you miss Poisson process. Okay. In CS1, most of them they said me they didn't understand Poisson process. Okay. Even whatever I explained last time, that's not sufficient. It will continue in every class. Today also I will take half an hour because we'll go back. I will first show you what is Kolmogorov, all this. Then once you get the idea, you will get that feeling, wow feeling. Okay. Then I will start from scratch once again. See now, we want to predict. Now the time is 6. I mean, I started then. Now, suppose it's 6:55 or 6:50, whatever, 6 p.m. We want to predict for 7 p.m. What will be the mood? Okay. Now, Amit says me, Anu says she will come now to me. She has some problem. But earlier it was decided that tomorrow will be the meet. But today she is coming now and you have to answer me. Can you answer? I say yes. I say yes. So we need a continuous time stochastic process so that I will be able to say the next instant what will be the mood. Is it possible at all? Is it possible? How it's possible? It's possible, right? Newton, Lagrange, all those have given calculus. Even we have studied in CM1. We have studied in CS1. If you remember, in CM1 also we talked about small time. Small time. Remember the delta. Okay. The force of interest. Remember mortality, intensity, alive and death model. I will bring all those here. If you studied CM1, those things you used. Here you are really studying. Anyway. Okay. Let me bring this example for you. Okay. I have a word file. See this example. This one will take here 0.01 mu. Mu means if you must have studied CM1, right? That mortality. Okay. Transition intensity. Very small time. Even it's not 1 second. Next instant. What is the mortality? What is the mortality? What is the transition intensity? Okay. From alive to dead state, I will bring the state concept now, mu 10. Before that, I will give another example now. See, state 0 is working in the company, leaving the company. One is leaving the company. Now, what you will model now? Okay. Now, suppose this is the company. This is the company, and someone is working in the company. Okay. Someone is working in the company. Now, people are working, right? People are working in the company. And now, the manager of the company, the owner of the company wants to know how many will leave the company. Okay, how many will leave? Zero to zero statements what? Working in the company. Zero statement, this is company, they're working. Okay. They are working in the company. This is the company. Okay. So there are two states. One state is working in the company, other state is leaving the company. Okay, working in the company, and this one is leaving the company. These are the two states. Now, what we want is after time t. Now, see, here comes main thing. Okay, when I said continuous time stochastic process, after time t, what is t? T could be anything. Okay, t could be anything. This is 0, suppose. This is state 0, state 1, state 0, state 1. There is no, I mean, one, see, directly we'll find 0 to 1 here. Okay, that means, according to this notation, we want to find P01T. Yes, this one, P01T. And I will show you the solution. Okay, forget about the. See, what we are doing is we are forming a differential Kolmogorov's forward differential equation. This is what I will teach you. No worries. Now I am only showing you. This is Kolmogorov's forward differential equation. I am introducing through the problem. What is 0? That is a state. What is 1? That is a state. How many states are here? 2 states are here. What is 0? Working in the company. What is 1? Living in the company. Continuous time stochastic process. Employees are working in the company. They can leave at any time, right? They can leave at any time. It's not that they will leave only after every month or every year. Okay? They will leave at any time, right? So, what we are finding is at time t, t could be anything. You find after 3 days, 4 days, 5 days, 3 days, 3 hours. I mean, living means giving an application. Okay. I mean, giving the resignation letter. That could be any time. That could be any time, right? That way you can think. So, what is the answer? See, I will show you the answer. Okay. So, this is Kolmogorov's forward differential equation. Why calculus comes here? Because wherever we talk about infinitesimally small time, okay, you are observing a car is moving. Okay, if you want to know the instantaneous velocity, the velocity at any point, suppose someone is watching on a tree, someone is there and watching. Suppose I say I travel every day from this place A to B in 3 hours. Okay, 3 hours, it's 120 kilometers. Then people will think that, okay, 40 kilometers per hour, that is the speed, that is my velocity. I'm traveling at 40 kilometers per hour. How about somebody on the tree watching me at an instant? Will I be traveling today at 40 kilometers per hour? Maybe not, because there might be traffic. Okay, there might be some person passing by, crossing, zebra crossing, or maybe it's an open road. I'm traveling at 80 kilometers per hour. See, that velocity, that was only average velocity. We are talking about instantaneous velocity. So how can you know? That's where you have to apply differentiation calculus wherever you want to know in the next instant. Okay, then you have to use that instantaneous concept. Okay, there calculus comes. So here calculus will come, differentiation. So how the derivation also, it's very easy. It's only 5 to 6 lines. If you don't require, that's a separate thing, but it used to be, because see, I proved here. I'll show this after this one. Okay, so you have to form a differential equation. I'm clearing everything. Okay, even if I don't take a class, I will share notes, you will be able to understand. Why live class? Because I wanted to explain the concept. Okay, understand the concept. See here, 0. What is 0? 0 is presently working in the company. Okay, done. Now 1 is leaving the company. You form a forward Kolmogorov's forward differential equation. Okay. How can you form the forward differential equation? There is an equation, there is a derivation. You just follow that. I'll explain you. It will take 2 minutes time. Acha. In the differential equation, if you see, what are the things you have? Now see, we have P00T, P01T, P, this is 0.01, 0. Again, you might ask, this is a problem. That's why it's 0 to 01 given. Okay. These are transition intensities. I will explain you what is intensity, what is generator matrix, what is transition matrix, everything I will explain today, the concepts. Okay. Now see the answer. First of all, I will take you the answer. What insights you are getting from here. Then we'll go through the question and all the theory, whatever is there. That way you will generate interest. Now, this means what? This means what? This means probability 0 to 1. 0 to 1 means given that you are at 0, what is the probability that you go to 1? Means you will leave the company. At time t, you can take anything. Okay. Maybe I like 7.3, 9 point, whatever you want. Okay. And then here we need to define time. Okay. Unit time. Unit time, suppose, let me write unit time. Unit time is because the intensities are defined per unit time. That is called rate. Okay. Even if you see mu, mortality in CM1, that is mortality, whatever value is given. But that is instant, but measure in 1 year. Okay. You need an interval to express. At a point, there is nothing. So here unit time is suppose 1 year. We are talking about 1 year. This is the rate per year. Okay. This is the transition intensity per unit. Again, what is transition intensity? I'll go to that. Okay. There is a concept of generator matrix. You must have studied transition matrix. From transition matrix, we will come to generator matrix. Generator matrix will give you all those, like transition matrix probability, or generator matrix will give you all the intensities, all the force of transitions. Okay. We'll go to that. But see what it gives. I want to know what is the probability that in 7 months time, 7 by 12, what is the probability that an employee will leave? But see, what is the rate of joining the company? Joining 0 to 1 means what? Leaving the company. Okay. 1 to 0 means rejoining the company. Okay. So, if you go by this, 1 in 100 leave the company, and 10 in 100 join the company according to this. So probably this is not an appropriate example in this case. So we can say something like this because they are again coming back. Okay. We don't have a third state also. We can't connect. So 1 leaving the company in a year, 10 are joining the company from state 1. Okay. Is it possible? Not possible, right? So we have to change this to 001, 0.001, 0.10, 0.001. Or we'll do one thing. Anyway, this is greater, right? 0 to 1. 1 e power minus 0.11. E power minus 0.11. Okay. Minus 0.11 e power. E power, right? Okay. E power minus 0.11. Done. Multiplied by t. So I'll multiply t 7 by 12. 7 divided by 12 multiplied by minus 0.11. 0.11 is equal to this number I have to take. Okay. So minus 0.064. Minus 0.064. Okay, I got it. Probability 1 minus 1 multiplied by minus 1. I got it. Divided by 11. So sorry. I'm so sorry. I'm wasting your time. Minus 0.11 multiplied by 7 by 12. 7 divided by 12 is equal to multiplied by minus 0.11. Okay, this much. Even if it's not correct, we'll accept e power minus 0.064. E power minus 0.064. Done. This much are done. Then 1 minus 1 is equal to done, multiplied by minus 1, done. Okay. So I got this divided by 11, divided by 11. So this is minus 0.15, minus 0.15. Okay. So that way you will get the probability. So what we will do is this example I have to change, because my outgoing is people leaving are 1 in 100. 1 in 100. Suppose 100 are working, 1 is leaving in a year, but 10 are joining. Okay. But because we are talking about living and joining state, 10 can join when 1 is leaving. Okay. That way you can find, see, we can interpret this way. We can bring, even I can take it as other ways also. I will show you my example. So what is important is when you solve Kolmogorov's equation, it can give at 0.1, 0.2, 0.25, 0.257. At any point you have an answer. Remember, in Markov chains, we had answer only after 1 step, 2 step, 3 step, 4 step. Step could be 1 year, 1 month, 1 day, 1 hour, it doesn't matter. But step concept was there. Here, not step. Here, every time you are getting answer. But for that, you need to solve even if you accept this one, you can find all probabilities. So you need to solve Kolmogorov's forward differential equation. Why 4 are there? Yes, sometimes this will be easier than the other one. Sometimes integral equation will be easier. That is a separate thing. But this is one of those 4 equations we use. Okay. Now you have to form differential equation. How can you form differential equation? That's easy. Acha. Here you will have this piece again. I mean, this is not our concept here starting now. This is P and this is P's are here, mu's are here. Remember, this is the most important concept of this. Mu's are here, P's are here. Now, remember in all these problems, mu's will always be given. Okay, here you see mu's are given 0.01. Okay, and this one is sorry, p's will be p's what, see, we found p, mu's will be given mu 01, mu 11. Okay, mu 01, mu 01 is given here 0 to 1. Mu, how, I mean, how, where you get this, that is a question. Okay, remember I said in Markov chains you need to get it from the past realization of the stochastic process. See, stochastic process is a model. We are here, the past we use, that way we do that. If you ask me where you get these values, okay, these mu's, because ultimately we have to find p here, these mu's also you need to estimate. How can you estimate? That is through statistics. Okay, there is a chapter that joins Markov process, Markov chain to Markov jump process. In between, there is a small 3-page chapter. Okay, if you go through that chapter, there we have everything like censoring also, type 1 censoring, type 2 censoring. If you have gone through, remember what we do there? We just get the intensities. Okay, we get the intensities there, transition intensities. Okay, the force of transition, the generator matrix values. I will go to that and I'll explain. Okay, so these you will get again. If you are doing modeling, you have to do it. Okay, these things you have to do it. Now, Kolmogorov equation says if you solve the differential equation, then only you will get this. So you have to form the differential equation manually also. Manually means what? By first principle. Without forming this one also you can do. I mean, you have to write a big one and you can solve. But ultimately you are solving this differential equation, right? Directly equation you write, then you make a differentiation from the first principle you do, or you can use this differential equation. Now, when you solve this one, instead of one period, you will get after one, every instant you want, you just put t, get the value, put t, get the value, one formula. Okay, that formula. Acha, you are solving a forward differential equation. Now, these are again from estimation you will get. How you get from estimation, I will explain you. And this is a part of a generator matrix. Let me write it here, generator matrix, so that you will understand. This is the generator matrix, and here we'll write 0, 1, 0, 1. This is mu 0, 0. Mu 0, 1 is given here, 0 to 1, that is 0.01. and 1 to 0, 0.10. 1 to 0, 0.10. And remember, these will not be given. These are the negatives of this. Again, there is a proof here. We'll do that. So these the diagonal elements are the minus of all the other summation. Here only two, so I'm writing minus 1 0. Okay, these are the generator matrix elements. Okay, that means these you have to estimate uh, whatever way. That's a wonderful way it's given. How can you do that? Okay, you need to observe. Actually, time spent under observation, you have to observe. Okay, when you observe people now surviving, when death will happen, when censoring will happen, using that data, we have a likelihood function. Okay, from that likelihood function, you will estimate this. That's a chapter. Okay, one class is required for that. I must have a recording video, or I will take a live class if you require. If you write in the comment, I will take a live class also. Okay, now this. So mu's you know. Now we have a equation for C. Mu, all mu's are put here. Where is the solution? Okay, now I will show you the solution once only. We will not discuss the solution here today, but I will show you one. See, this is the, oh no, this is not. I didn't bring. No, no worries. So, I mean, solution is simple differential equation solution only. Okay, you change it, make everything to, it's like this. In this equation, what will happen is finally you will get a equation like this: dy by dx, linear differential equation, plus some py is equal to q. We need to solve this kind of an equation. See, when I say y, when you solve this equation, you will get y. So y here is this P01T, that is why. Okay, so P00 was there. Using, because total will be 1, using this they transfer to P01, here P01, here in terms of P01, here in terms of P01. So y is the only variable. You solve this, it's a simple one, anyone can understand. It will not take more than even if you are new, half an hour. Okay, so you get y. So our ultimate is to get y. To get y, you need to solve a differential equation, that is forward differential equation. That equation you need to form. How to form? Yeah, those things what we'll study, it's very easy also. Okay, their recursion is required, their a kind of understanding is required. Okay, that will apply everywhere in all four kinds of equations I said. Now let me go here. Now you need to know Anu's mode at 7 p.m. Okay, at 7 p.m. Now what we can do is, we have to, for that, we have to find this P probability H. Suppose you name 1 to 2 states, 1 to 2, 1 to 2, 1 to 2, 1 to 2, that way. Okay, I'll write 1 to 2 in time. Okay, this is time, not always starting from here. We are here, right? Suppose we are at 6:30, we want to predict at 7. So in half an hour, half an hour means what time I will write? It depends. What you write, what is your unit time? Unit time, it depends. Rate, okay? Suppose you are, you write it 1 year way, 2 year you observe, okay, whatever way, 2 year, it's a continuous time, but you are observing, you have decided your unit time. What is your unit time? If it's 1 year or maybe 1 hour, I will write half. If it's 1 day, we started with 1 day, right? 1 day means 1 hour means 1 by 24, 1 by 48 hours. Okay, that's half an hour. So what is the probability of moving 1 to 2 after half an hour? That's what you can find. This probability will give you. So now if C is at 1, what is the probability that she will be said at this time, going to this, from this to this? Occupancy probability means we started at 1, happy, she will continue to stay in happy. I mean, she might go to somewhere, that's a separate thing. There are two concepts again. I'm not, that's P11 bar, but we are not interested in that. It doesn't matter. Oh, if she was not happy during some time, that's fine. Okay, let's not worry. But P11 will find T, P11T. That means at the time we observed, she was at 1. Okay. Yesterday, if you have information, you write that, no problem. And the time we observe, I mean the total time you have to write, okay, 1 to 1. No change means this is called occupancy probability. Suppose I've started a class, Okay. What is the time I'm staying in this state? From this state, then I will go to jump to another state. Probably I will go to the market. Maybe that's another state. From there, I will come to my dining table. That's another one. That's another state. So I will be changing states. My occupancy probability. I was at one. What is the probability that I will be in one? But occupancy, when I say bar will be continuously occupying. But when I say only one, I mean, in between, whatever happened, you go to 2, 3, but when we watch again, that time you should be at 1. So presently we are not interested what happened in between. So we'll use only 1. Okay, no bar here. We'll go to bar also later. Acha, this is what you need to see. This is a continuous time now. So that means we'll do everything from scratch. All the 4 differential equations, probably, if I explain in details, it might take 2 classes. Okay. So all the problems you will be able to solve if you understand conceptually. Now, see, this one I will bring, and then I will leave it here. I will continue from the next class. Meanwhile, I will switch to, because we have to start from scratch, I will switch to a Poisson process, because that way we'll connect. Without Poisson process, I can teach here, and although you will be able to solve problem with today's concept, whatever I already taught, but it's not only solving the problems, right? You need to understand what's happening. Now, suppose this is healthy. This is healthy state, and this is alive and dead, do we say? Alive and dead. I remember in CT1, CT5, CS, CM1. Alive and dead, alive and dead, alive and dead. These are the states, alive and dead. Okay. Now it's not that alive and dead, we only say someone will die only after each day or each year or each hour. Nothing like that. One can die at any time, right? Suppose you want to know the probability that the person is dead at this, okay, and now alive here. You need to know this, okay. So that's how we'll find, that is P. That's what you will get when you solve a differential equation forward or backward, or solve an integral equation forward or backward. There are 4 options for you. That's how we'll get once you solve alive to dead. You'll get it at time t. You put t here time and you get it. But like Poisson process, I will go to Poisson process now. Here to solve this, you can solve, like, because if you form a differential equation, again I'm repeating, there you will get p's and mu's. Okay, p's and mu's. P's differential equation will be there, you solve, you will get p, and this is what we require. But there is something mu. Mu's are the transition intensities. What are mu's? That I will explain. I will take 1 minute, then I will leave it here. Instant, again I'm talking about instant now. Okay. And if I teach you Poisson process, again this will have meaning. Now, what is the probability of a transition from A? Do you remember this notation PA to D? In a very, very small time, infinitesimally small, we say. In a very small time, what is the probability of making a transition? And this notation, if you remember, it was in CM1, it was mu. Okay, mu. Mu I to j we write, you can write A to D. We never wrote something here, but yes, it's mu. Mu is from alive to dead, not in some time like 1 minute or 2 minutes or 3 minutes. Again, I'm saying you, one benefit is when you are using continuous time, you can use it for discrete also. You can use for continuous, but for discrete time, specifically for discrete. Okay, you can observe a continuous process, but you can analyze every day or every year, not a problem, or every minute, every second. I mean, it's your choice. But if you are taking a discrete, only you can analyze for discrete times. That's all. Now here, in a very small time interval, what is the force of transition intensity? So what is this? This is not probability. Okay. Now instead of this matrix, big matrix, this is your one time period. Okay, unit matrix. This matrix is called transition matrix. Here we have probabilities. Remember, we wrote 2, 2, right? 2, 2. So here we have probabilities. Okay, and this is called, these 4 probabilities are there. Going from here to here, here to here, here to here, all these probabilities are there. Now, if you take small time, these are no more probabilities. Okay, let me write probabilities. Let me write probabilities here. Suppose these are probabilities 0.7, 0.3, 0.2. I don't remember, 0.8, 0.2. Now these are transition probabilities. Transition probabilities in the sense, sum of all these values will be 1, all are positive. Okay. This is transition probability matrix. Now this is called generator matrix. Generator matrix. Generator matrix means same will write A, D, whatever states here. A, D will write. But here what you are doing, here you are observing there is 70% probability that alive will be alive after 1 year. Suppose unit time is 1 year. This is there anyway. What about this? Alive to alive, alive to dead in the next instant. Okay, this is what you are finding. Alive to alive, alive to dead in the next instant. That is your mu, whatever we studied in CT5, CM1. CT5 means CM1 part 2. Here, this is what we found, A to D. But that was a one-state model. There was no such D to A not possible, right? That was a, so we can write 0, 0, this is minus mean. I mean, that's CM1 thing. But what I'm saying is, these are called generator matrix for any two state. Generator matrix means will not worry about these two, A to D, D to A. If D is not death, okay, any two states A and D. So these two you have to estimate from your sample. I mean, you need to start observing people. Okay, the birthday concept is there. Okay, you start observing from a birthday. I mean, if not are available, there is a concept of X plus AI, X plus B. You start observing the time spent under observation, all that you need to do. You need to form a likelihood. You need to differentiate. You have to solve. So that's a, I mean, probably 2 hour thing you can complete. And if you want, if you write in the comment, I will give a live class for that also. But I don't intend to give at this point now. Okay. But that's a quite thing. So those things you will get from these again. I always teach in CM1. When I say A to D, when I say this is mu kind of a thing, alive to dead, okay? Again, I'm saying if you go and see your actuarial table, mu's are for a one instant, but they are not instant probabilities, death probabilities. They are not. Okay, even the intensity that is measured, like always I say, suppose I'm traveling. Okay, someone asks me at what speed you are traveling, I say 40 kilometers per hour. Why I'm saying per hour? Why I don't say at this instant? See, we need an interval to measure. That is interval mathematics. Continuous mathematics can't be measured by point. Using point by point, we have to use interval by interval. So, though, see, if someone says at what speed you are driving, I'm saying, my friend, I'm sorry, I'm unable to answer at what speed I'm driving now because instant point-wise mathematics, it's a continuous mathematics. I will be able to say if I continue to travel at this speed, I will cover 140 kilometers in 1 hour. That way only here also. Mu, if you see, mu will be very close to P. You go and check actual table. Mu and P, they are very close. P is probability of surviving for 1 year. Q is probability of dying in 1 year. Mu is dying in one instant, we say. But they are almost same. Why? Because the measurement is for 1 year both. Okay, by chance, if you don't know this, you do that. Here also, though instant I'm saying, but the measurement will be in an interval. Okay, that is something, some concept you need to know. Anyway, so these again, that's through chapter. So these, so the difference, what I'm saying is that the differential will contain both P's and mu's. Mu's you will get from that statistic. Okay, that two-state model name was there. The name of that chapter. Okay, from that, from your observation, you have to estimate the discrete time. In discrete time stochastic process also, those there is something, okay, the exam question you get, those also you need to estimate from the past data. Okay, those things you need to estimate. So now you solve, you get P, work is done. Okay, I explained you the concept, but these four are there, that might take one class. And there is non-homogeneous also. Okay, non-Markovian also. It's not that everything is Markov. Suppose you go to a doctor, okay, you say I have fever. Doctor will ask you how you felt yesterday. You said, I had no fever or I had fever, and immediately doctor will give medicine. That's wrong. That's wrong, terribly wrong. Because normal doctors, they never do that. Immediately they ask, since how many days you are not feeling well? You say, since last 1 month, last 15 days, I'm not feeling well. Then doctor says, oh, 15 days, probably you have a typhoid. I have to go for blood test. He wants to know the full history, not only 1 day information, right? So it's not that everything is Markov. Stochastic process is our framework. Markov, see, whatever we are doing, here we are using Markov. You go to time series. Our framework will be stochastic process. Okay? And temporal. Temporal means time. Dynamics. We are modeling, do that. Spatial, you will get. Spatial also, a lot of applications are there. We don't do anything here. But the framework will be stochastic process. We will not be using Markov, but we'll be using that. Time series is, I mean, time series will use ARIMA process or ARMA. ARMA is not always Markov. AR1 is Markov. AR2 process is not Markov. Again, we'll go. Time series I will teach live. No worries. Time series throughout life. Time series such an important one. Okay. Awesome. Acha. Now, where we are. So, mu's you have to estimate. Remember here in continuous time stochastic process, P you have to find ultimately. You will have a differential equation, forward, backward, whatever. Their differentiation and integration will be there. You solve, you get the P. That's all. It's over. Then any instant you predict the probability. This is probability. See, this is there is no more mu. That's what I want. I mean, you must be thinking why I'm explaining time and again the same thing. No, same thing. Here, this is P. We're saying probability. This mu, you can't say mu. Mu will use. Okay, P will find. It's a magic. Okay, Taylor's theorem. It's a magic. Do you know what Taylor's theorem do? That's a magic. That's not this class. So I'm not explaining you Taylor's theorem. People they never think on that. That's a magic. Kolmogorov equation. It's a magic. Okay. So math magic. Anyway, now we'll start from scratch. We need to understand actually Markov process. Okay. Remember, Markov chain I've completed in last whatever 2 to 3 classes I must have taken, starting from stochastic process. Today also half of the class. And I explained the continuous time stochastic process, fully concept, how to deal with it. Now, from scratch, see, this problem will take so much, see, but with the problem I will teach. Probably will pick up a problem. This one will do this. Okay. The number of claims arriving at an insurance company follows a Poisson process. Poisson process. Again, what is Poisson process? It's kind of a stochastic process. Okay. From stochastic process, that's general framework. To Markov process, with one step information we are using. From Markov process, again, there is a link between Markov and Poisson. I'll go to that. But come to Poisson process. Poisson process is a counting process. You must be knowing counting process definition. Counting, you just count. Counting can never be negative. Okay. But in Poisson process, we have special properties. It's a counting process. Okay. Plus counting process, whatever properties. Okay. Counting means not necessarily it will start from 0, but it will be always increasing, at least constant. Okay. Suppose the number of students coming to the class. Now 10 are there. Okay. 11, 12, 13 coming. Suppose nobody is leaving. Then you go on counting, it will increase or stay constant after time, right? Now, first of all, remember, Poisson process, when we say the time is continuous, I'm writing time discrete means don't think that it's discrete time. It's a continuous time stochastic process. Okay. Then you will ask me what is the difference between Poisson and Markov. Yes, I will tell you. Surprisingly, magically, whatever you say, uh, Yeah, the waiting time pattern for Markov, everything, it will be like Poisson only later. I mean, that combination is there. I will go to that in the next class. But yeah, let me tell you through this example. It says, see, Poisson process always starts at 0. Okay, Poisson process starts at 0. Let me go there. We'll use another ink. Poisson process starts at 0. I've written 0 here. And it says uh, 5 claims a day. Day means, remember, the rate when we say it's day, every day 5 claims. Every day 5 claims. I must have explained last time. Every day, okay, 5 I will take, I mean, I can't write all the states here. There will be so many states, but yes, I'm right randomly. Don't count here. Okay, 10 this way. Okay, every day 5 claims. So the gap is 1 day. It's a continuous time. 15, 20, that way it's going. Okay, suppose 15 is here, it's increasing. This is a Poisson process. Okay, now before going to this problem, suppose I've started my YouTube class today, live class. Will it follow a Poisson process? Even the motor insurance claims can be modeled as a Poisson process. You find it from your material. The motor insurance claims can be modeled as a Poisson process. What is the meaning of that? If you don't understand, how can you work in insurance companies tomorrow? Right? It's very crucial. I'm spending time repeating means not for any reason. You think I started my YouTube class. Will it follow a Poisson process? When I say Poisson process, according to time, okay, according to time, the students are joining one by one. Will it be a Poisson process? It's a counting process. Students are increasing. Okay, probably. I mean, CS2, it's a very highly specialized. Maybe you will not see more number of students. But yes, if not today, tomorrow they come and they watch. That's a separate thing. The time is there. Suppose from now I started my YouTube class live. I will count for 30 days. Students are coming and watching. I will see the watch time. Will it be a Poisson process from time to time? Suppose every day I will see how many students they viewed. But live, if you say now watching, students are coming and going. Going means that will not be a Poisson process. Remember, it's a birth process, not a death process. Okay. Only it will increase. It can never decrease. Okay. Birth process, not death process. Somewhere where people are coming and going. Suppose you talk about a mall. People are going and they are coming. If you calculate the net number of people, that will not follow a Poisson process. Forget about coming people. If outgo is there, that will not be a Poisson process. Okay. So now think that I will not watch live. I will watch for 30 days every day. Okay. Every day, suppose I get 10 views. Okay. 10 means ideally, that you have to know lambda. Lambda is the rate. Rate means every day. Lambda is 10. 10 every day. Okay. So not only 10 every day, but also if you take a very small interval, like here I'm drawing, if you take a very small interval here to here, I explained this one. I will not spend a lot of time today on this. If you see a very small interval, either one student will come to watch or no student will come to watch. Is it okay? This is not okay because YouTube sends notification. Suppose Mr. Beast will make a live, many people will come and join immediately. So how it's possible? See, Poisson process means if you consider a very small time interval, infinitesimally small time interval, only one event will happen or no event will happen. Two probability is very small. So suppose YouTube sends notification to thousands and people will come and join. So in one instant, 1,000 joining. Then how it will be Poisson process? So Poisson process is not only like this is also homogeneous. Right? 5 are coming. Okay, it's not like 5 are increasing. Okay, constant rate lambda. Variable also will do that. But let's keep it here. We are talking about this Poisson process. So if YouTube sends notification, that's not allowed. Okay, doctor, you take appointment, go to meet a doctor. That's not. Even when we talk about waiting time, that is a link with this Poisson process. From Poisson process only we will find waiting time. Individually, if you studied in CS1 or somewhere else, that's only for learning, solving problems. Because waiting time concept will come here. I will introduce today. This follows a Poisson process. The number of people they arrive there, they should be random. Okay. If a doctor, like a clinic, doctor goes and opens. Okay, it's a clinic. Nobody has second appointment. Randomly sitting and people are coming. That could be a Poisson process. Motor insurance, motor car claims follows a Poisson process because it's not that immediately two persons will claim within 1 second. Because suppose there are intersections in Delhi or Bangalore, there is an intersection, one accident happened. There is another in some intersection, one accident happened, and both called at the same time. Okay, give my claim. I met with an accident. They reported. I mean, previously it used to be physically. Long year before, nowadays you go to a repair shop and make the claim, and you can report. You get online also. Everything is possible. What I'm saying is, at the same time, in a very small time, 2 3 accidents happening is very rare. Okay, you small intervals, even in this interval, suppose there are 1,000 steps. Okay, an old man or you are going every instant, either you go one step or no step, you take rest, you are tired, or you take one step in one instant. 2 step probability is very less, right? Some they jump. 3 step probability is also there. Order of H we write very small. We are not saying 100% zero. This is actually Poisson process. NT follows Poisson lambda T. See how useful it is. Even you must understand what is a Poisson distribution from this. What is a Poisson distribution? Suppose 2 days are fixed. Suppose 2 days are fixed. And lambda here, lambda is 5. Suppose you are worrying only about 2 days. You are not worrying about 10 days, 3 days, 4 days, 5 days, 10 days. Okay, 1 year. You are not worried. You are only thinking about 2 days. Okay, in 2 days, NT I can write N2, N in bracket 2, or directly I'll write N, or X I will write. Okay, X. What is X here? X is N2. What is N2? I'm talking about 2 days only, up to 2. Okay. X will follow a Poisson distribution. Suppose you have seen a question in CS1 like this. My lambda is 5, 2 days is 10, lambda 10. Okay. So what we solve in CS1 is, even in CS1 also Poisson process were there, but importance was given to binomial Poisson distribution. X follows, X is a random variable, it's static modeling, no time dynamics is here. Okay. X follows Poisson distribution with mean 10. That means 2 days, forget about this. 2 days already fixed. Nobody will talk about 2 days. Okay. Only question will be X follows a Poisson distribution with mean 10. 2 days, I mean, because I derived from here, I'm saying 2 days. Forget about 2 days. We are not talking about time only. Okay. So X follows a Poisson distribution with mean 2, mean 10. What is the probability that 4% will come in next 4% will come next unit. 2 days means 2 days you go. Next 2 days. That's all. That way we do Poisson distribution. Okay, there is no such time. You go through that Poisson process, Poisson distribution. Okay, there is no time constraint. Time we don't say. I explained because I derived from this Poisson process. Okay, so if you fix, suppose even not necessarily the diagram because it's continuous time. You fix here, this is a Poisson distribution, N0. What about N1? N1 is a Poisson distribution. What is its distribution? Poisson 5. What is the distribution? This Poisson, this is 5. This is anyway, N0 is 0. It starts from 0. What N2 will follow? Poisson 10. Poisson 10. What N3 will follow? Poisson 15. What N half will follow? Yeah, that is also there. It's continuous time. N half will also follow a Poisson process. Lambda is 5. 5 multiplied by 0.5. 2.5. At any point, that means you want to study up to 1.5. At any point you can find. Okay. Now let's solve this problem. Then we'll go to waiting time. We know that NT is a Poisson process. Now, what problem you are solving here in this example? You are finding, what you are finding? What is the probability that the company will receive 4 claims tomorrow, 40 claims in next week? Okay. So tomorrow means we are talking about 1. Okay, N1. So we are finding probability that N1 greater, less or equal. N1 5 claims next day. Average of with an average of 5 claims. What is the probability that company will receive 4 claims tomorrow? This is what you are finding. Okay. N1 follows. We know N1 you write change to X now because it becomes a random variable type. Poisson 5 given. Use Poisson 5. You do this e power minus lambda lambda power x by x factorial over. This is the random variable x. N1 is random variable. Next, 40 claims in next week, 7 days. So part 2, N7 is a random variable. As I already said you, stochastic process is like a train. Every bogie is a bus, that's a random variable. N7 follows Poisson 35. Now you need to find 40 claims. Probability that N7 is equal to 40. You know lambda 35 here, like CS1, Poisson distribution lambda. You know X, you apply the formula, you will get the answer. Now we'll go to waiting time. Achha, now what we are saying, 5 to 10, okay, in one day. And I said you, in very small instance, one only possible. That way, what will happen is, 5 claims means maybe 10 to 11 you got 1 claim, 2 to 3 p.m. you got 1 claim. Again, they say 24-hour hotline, all that. 6 to 7 p.m. you got 1 claim. Now it's online. I mean, anytime you can apply. Okay. So, in a very small time interval, 1. That way, suppose it's 5 to 10, 5 to possible. I can make it 5 to 1000 also, 10,000 also. But 10,000 instances are there, 1 that way. Sometimes 2 also it's allowed, but not that way. Now, what I'm saying is waiting time. Waiting time means, I mean, suppose it starts today, okay, 10 a.m. to 10 or 8 a.m. to 9 a.m. to 9 a.m. Today 9 a.m. we started. It's at 5. Tomorrow 9 a.m. it will be at 10. Today 9 a.m. when I started. Up to what time there will be 9 a.m.? Okay, it's waiting time. Till going to 6 claim, that's waiting time. Suppose I'm giving a class. I've started my classroom session. I'm in the class and I'm waiting for the first student. That is called T naught. T naught is waiting time when a student will come to the class. What is T1? T1 is waiting time, that is inter-arrival time. One student already came. How much time it will take so that the second student will come and join? That is T1, T2, T3, T4 that way. So all the waiting times from no claim to 1 claim to 2 claim, 2 claim to 3 claim, you consider ATM. In an ATM, suppose you are standing and people are coming one by one. Okay, watch. The waiting time means the gap between 1 to 2, not from 1 to 2, 2 to 3, inter-arrival we say, right? All the waiting times T0, T1, T2, T3, T4, all are independent and they follow exponential distributions. And typically you get a proof. Even if you don't get a proof, you need to know, right? So now, waiting time means you are continuously here. The claim 9 a.m., 10 a.m., 10:30, 11, 12. At 12, another claim came. So now your state, you occupied that state. Now your state is changing. Because why I'm saying this is important, waiting time. Here in Poisson process, waiting time follows an exponential pattern. Surprisingly. In Markov also, Markov jump process, you will see, there also we'll talk about waiting time. Poisson process is a particular case. Poisson process is a Markov process, but not all Markov processes are Poisson. So what will happen? Surprisingly, I'm saying, Poisson process also, again, the waiting time, memoryless property, all are connected, okay? I'm not going to that now. Markov process also, there also have to prove once again that the waiting time will follow exponential distribution. But let's stick to this. Waiting time means it will go from 5 to 6 sometime, then 6 to 7. That way, so it will go to 10. Na? So 5 to till going to 6, that is the waiting time. Okay. Now, if you start from 0, 0 to 1 will be T1. In terms of notation, 0 to 1 will be T1. When you go to 1 claim to 0 claim, that will be, sorry, T naught. According to notation, T naught. T naught is the first waiting time from 0 to 1 claim. 1 claim now you have, 1 to 2 you will go. Not in a day. In a day you will increase 5 by 5, you jump. It's a jump process we say, right? You will jump from 1 to 5, you will jump. So T naught is no claim to 1 claim. Okay, that we'll find now. Now here you see, here no claim, here you have 1 claim. Okay. Suppose T naught is your waiting time. This is your waiting time T naught. Now what we are saying, if T naught is your waiting time, okay, what is the probability that this waiting time is greater than T? This will, T naught means what? You are waiting. I'm waiting to give a class, to talk to my first student who will come. I'm waiting. Suppose that waiting, it's already 5 minutes over. Okay. Now someone calls me and says, how many students already came to your class in 4 minutes? It's already 5 minutes, nobody came, right? So what is the probability that T0 is greater than T? T0 is my waiting time. That means T0, at T0, after 5 minutes only, someone will come. This is not the typical state, okay? This is the waiting time. That means it's like this. In the diagram, 0, 0, 0, 0, 0, all time. Suppose 5 minutes, 4.00000009. Up to this, it was 0 only. Okay, it was 0 only. This is T0, I've taken 5, right? 0 to 5 minutes. T0 is 5. Okay. 0, it was 0. It will make a transition here. Okay. Now, before making a transition, in the instant, what will happen is, here, this time could be 4.999, whatever, because at 5, I'm saying it could be 5.1 also. I've taken 5. Okay. So what is the probability that T0 is greater than T? That means what? If I go to that T could be any time here, T time here, where I am. Because you see this, interesting. Because I already said that T0 is the waiting time. That means T0 means what? T0 is a notation to get the first claim from 0 to claim. That means first claim has not come because T0 is greater than T. By time T, this is not capital T. This is capital T naught. This whole is capital T naught. Now, this time if you see, I must be at 0 only. Because I transited only at T0, which is 5, I will say. So before 5, if you take any point, before 5, because T small t is less than T naught I have written, it's before 5, because T naught I have taken 5. So how many claims I had? I had 0 claim. That means that is equivalent to, up to time T, how many claims I got? I didn't get any claim. Remember, N0 is 0. I'm making it clumsy for you. Let me write here. N0 is 0. That is, we are starting from 0. So NT is 0 because up to T time, because T is less than T naught, and T naught is the time when I will get my first claim, my first student. So before that, nobody has come. The value of the process at time small time T, if T is less than T naught, is 0. Okay. But NT follows Poisson lambda T. Lambda is the rate. According to that, e power minus lambda t power x is 0 here, divided by 0 factorial. That is e power minus lambda t. So I got, this is minus lambda t. That means what will happen? I will make 1 minus. then I will get probability T0 less than or equal to T. That is 1 minus probability T0, that is 1 minus e power minus lambda t, right? And this means this is exactly capital Ft of T naught, 1 minus e power minus lambda t. And then if you write density function of T naught, that will be e power minus lambda t. This implies T naught follows. This implies this. This implies, let me write a box here. This implies T naught follows exponential lambda. This is waiting time. And you can use in a problem. There will be problem. Waiting time follows exponential lambda. Surprisingly, in Markov also the same thing. The only difference is lambda 1, lambda 2, lambda 3 will concept will come. We'll go to there. But here T naught, the waiting time to the first claim. The waiting time from first to second, that is T1. All these random variables will follow exponential distributions. If you are in a Poisson process. That's all for today's class. Class is over now.